So this section is on waves and light. It's going to be a bit of a long section. We're going to cover several topics, so just bear with me. Waves are critically important in science. That's why we're going to spend a little bit of time talking about them in a variety of ways, some of which you're familiar with. For example, all of the information we get about objects outside our solar system comes from light. Light's a wave. This stuff is collected by telescopes, and we haven't, while we send people to other objects inside our solar system, where we send spacecraft who collect data more directly, everything that comes from outside our solar system, 100% of it, comes from light. And so we have to understand light to understand what's around us. We also, for objects inside our solar system, we collect a lot of light. Most of our observations are with telescopes. We do send probes to various places, but even those are often just using optical devices, telescopes and cameras to collect data. Nearer to home, almost all of the information collected by geologists about the Earth deeper than a few miles below the surface is from sound waves instead of light waves. They do this by using seismometers and seismographs to understand the vibrations of the Earth. These are sound waves traveling through the Earth that are detected by these seismometers, and we'll talk about this at some length soon. You're familiar with various types of light and sound waves that are used to look inside human bodies in a variety of ways, from sonograms to look for babies, or to study the inside of your heart. They're now used to look at coronary arteries sometimes, and various other objects involving inside your body, kidney stones, all kinds of different things can be. Sound waves can even be used to break up kidney stones, not to just look inside. So understanding how these waves work is very important. Similarly, with optical, instead of sound, with light, X-rays and PET scans and MRI images are used to look inside our bodies and to do things inside our bodies. And understanding how they work is extremely important. These types of tools on the human body are non-invasive, and they're often much, much safer than having to go in and explore inside a human body to see if there's a problem. So let's do some waves basics. A wave is a traveling disturbance, really. That's the most general definition. There are two basic types of waves. A transverse wave is a wave that oscillates perpendicular to its direction of motion. You should think of like a wave on a rope, like a sine wave oscillating up and down. The wave might be traveling to the right down the rope, but the oscillation is perpendicular to the rope. It oscillates up and down while the wave moves maybe horizontally, if the rope is held horizontally. Different from transverse waves are so-called longitudinal waves. These oscillate along the direction of motion of the wave. Sound waves actually work this way, but the easiest way to visualize them is with a pulse on a slinky. If you take a slinky and just hold it stretched out a little bit in a straight line, and instead of oscillating your hand perpendicular to the length of the slinky, just give the little slinky a pulse along its length, and you'll see a wave travel down the slinky. And so there are lots of these are the two basic types of wave: transverse and longitudinal. We'll be talking mostly about light, which is a transverse wave. We'll also talk about sound, which is a longitudinal wave. Light itself turns out to be a transverse wave consisting of oscillating electric and magnetic fields, and we'll just mention that briefly as we go. So here's a picture of a wave on a slinky. That's a longitudinal wave, and a wave on a rope. That's a transverse wave. So let's look at some properties of waves. The wavelength of a wave is the distance between like points on the wave. So the distance between peaks. So let's look here. And we can see that a wavelength lambda is depicted as the distance between peaks, successive peaks. We could have just as easily used the length as the distance between successive troughs. It's the same distance. Or say halfway up the ramp to halfway up the ramp, right? Or halfway down the ramp here to halfway down the ramp over here. Those are all the same length. And so what we usually say is the wavelength is the distance between light points on the wave. The amplitude of a wave is the maximum displacement of the wave from equilibrium. So let me see if I can put that in here again. If you look at this wave on the rope, as the wave goes down, the maximum, if the rope's just held straight, it runs right along the center, and so the maximum displacement is where the peak is, and that distance from there to the equilibrium position to the center line is called the amplitude. Now we're going to talk about the period of a wave. So imagine you're standing in the ocean and waves are going past you, say, past your legs. The period of a wave is the time for one full wave to pass by a point. So if the peak of a wave passes by you, the time from then till the next peak hits your legs is the period of the wave. So what about the frequency? It turns out the frequency is defined as the number of waves per second that pass a certain point. That's a little trickier to sort of explain, so I'm going to just do it by an example. So if you're in the wave and it takes 3 seconds, like we said a minute ago, for a full wave to pass you, so the period is 3 seconds, then 1/3 of a wave passes by you every second. Right? If it takes 3 seconds for a wave to go by you, then 1/3 of a wave passes by per second. Right? And so we say the frequency is 1/3 per second, or 1/3 hertz. A hertz is just another way of saying per second. And so we would say the frequency of a wave that has a period of 3 is 0.33 hertz. It turns out the frequency is just the inverse of the period. F is equal to 1/t. So the period was 3 seconds, the frequency is 1/3 hertz. You can do another example. You say, suppose the period was 5 seconds. If the period is 5 seconds, that means it takes 5 seconds for the wave to go by. So every second, 1/5 of a wave passes by you, because after 5 seconds, then a full wave has gone by you. And so the frequency is 1/5 of a hertz, or 0.2 hertz, if the period is 5 seconds. So we've defined now the wavelength, the amplitude, the period, and the frequency. We're going to define the velocity of a wave, or the speed. And so let's do this by example. We'll say, look, suppose this wave that we're talking about that has a period of 3 seconds has a wavelength of 5 meters. So if the period is 3 seconds, that means when the wave comes by you, when the second peak comes by you, it takes 3 seconds for the second peak to get there. Well, if the wavelength was 5 meters, that means that peak is traveling at 5 meters in 3 seconds. Since speed is distance divided by time, we get 5 divided by 3 is 1.67 meters per second. That's its speed. And so the speed is just the wavelength divided by the period, or lambda divided by t, or equivalently, since the period is 1 over the frequency, we can say the speed is the wavelength times the frequency. It's a useful tool. So here are a few examples. We know some speeds. So the speed of light is 300 million meters per second, or very close to that. It's like 2.9979 times 10 to the 8th meters per second. So we usually round it up and call it 300 million meters per second. If we converted that to miles per second, that's about 186,000 miles per second. That's almost 1 second to get to the moon. The moon's about 240,000 miles away, and so that's about a second, roughly, to get to the moon. A second, a third, maybe. For comparison, the speed of sound, which we normally think of as quite quick, is about 1,100 feet per second, or 0.2 miles per second. So the speed of light is 186,000 miles per second. The speed of sound is about 0.2. The speed of light is almost 1,000,000 times faster than the speed of sound. It takes sound about 5 seconds to travel 1 mile. This is why when you're outside and you see a lightning flash, you count to 5, and that's if you hear the thunder after 5 seconds, that means the lightning strike was about a mile away. When I was a kid, you were supposed to see if you could get to 15 so that the strike was 3 miles away before it was dangerous. If it was less than that, it was dangerous. Now they just say, if you can see lightning anywhere, go inside. In a vacuum or in air, all wavelengths of light travel the same speed. We use the letter c for the speed of light. C equals 3 times 10 to the 8th meters per second. And so we can write that speed equation that we had on the previous page. Instead of v is equal to the wavelength times the frequency, we can have c is equal to wavelength times the frequency, or we can say the frequency is equal to the speed of light divided by the wavelength. Those are equivalent ways to write the same equation. So when we're speaking a little more scientifically, we refer to light as electromagnetic radiation. It's really just a fancy way of saying light. It ranges in wavelength from miles to kilometers long for its wavelength. It could even hundreds of miles long for one wavelength, to, I don't know what that is, a quadrillionth of a meter, maybe something like that. This is about the size of the nucleus of an atom. This size, and of course it'll go smaller than that. There's no upper limit or lower limit in the wavelength of a wave. Using this expression that we came up with on the last page, that the wavelength, the frequency is equal to the speed of light divided by the wavelength, we can see you can have frequencies of 100,000 hertz or lower, up to 10 to the 23rd hertz, which is this number across the bottom, and higher. So there's a wide range of possible frequencies for light. All of these are detectable by us. The ones we see is a very, very narrow band of them in the 10 to the 14th hertz range. Most of these, the vast majority of these are invisible to our eyes. So this is a picture of the electromagnetic spectrum, and I'm going to try to we're going to talk about this for a few minutes. This is sort of the range that we're talking about, or part of it. You can look at the top here, and so this is, to the left is increasing frequency, to the right is increasing wavelength. That's a Greek letter nu, but it's what we would use an F there. Energy increases with frequency, and so energy of the light is increasing to the left, wavelength is increasing to the right. Here's names of these bands, which we're going to talk about in a second. So over here in the long wavelength range is radio, and then microwave, and then infrared, and then visible light is right here, this tiny little range with the rainbow here, and then ultraviolets, and then X-ray, and then gamma rays. And these are the bands roughly. And here are some tools and roughly where they fall left to right on this scale. Radio waves and microwaves, and a router, and then cell phones. These are in the sort of the radio wave to microwave range. This is radar. TV remotes are typically in the infrared, so it's night vision. Then we've got this visible range that we can see in, and then if you've ever had something glued in your mouth by a dentist, that's in the ultraviolet range. That's also the sunburn territory. Then you get X-rays or PET scans up in the gamma range. And these are just cosmic rays from space. So these are very low energy, these are very high energy waves. So we're just going to talk about these bands for a minute. I kind of want you to know the names of these bands, and you don't need to know the frequencies relevant to them, but you should know what order they're in. This is in order of decreasing wavelength, and so you should be able to name off these bands. So the radio waves are primarily used for communication. Microwaves are used for cooking and communication. 30 years ago they were almost exclusively for cooking, but now increasingly we're using them. Cell phones and things are using the microwave frequency range. Infrared is used for heating things. It's also used for TV remotes and stuff like that, so that's also communication. Look at here's the visible frequency range, right? It's 4 times 10 to the 14th hertz through 7.5 times 10 to the 14th hertz. But if you look at the range of these numbers from 100,000 to a bajillion up here, this is a tiny, narrow little band that our eyes are sensitive to. Right? Oh, sorry, here it is, a tiny, narrow little band that our eyes are sensitive to. Ultraviolet band is higher frequency than that, and it's often used for sterilization, or you can get skin cancer with it. Hopefully you don't want to do that. But they're often used for killing bacteria in water and things like that, exposing it to UV light. One thing, source of confusion for people, I think, is that if you put ultraviolet light or X-rays on something and then turn off the source of the ultraviolet or the X-rays, those rays they haven't contaminated the water or whatever they've hit any. Now, if it's you, they'll damage you, but you can drink water that's been hit by ultraviolet light or X-rays to sterilize it. There's no residual danger in food or anything that's been irradiated by these waves. They just kill stuff they hit, and then it's like hitting it with a hammer. Once the hammer has hit the food or whatever it is you're hitting with, when you take it away, there's nothing dangerous about eating that food as long as your hammer was clean, I guess. So there's no danger associated with eating irradiated food that's been irradiated, as long as you're not also eating the source of radiation. That's when it gets dangerous. So these are some frequency ranges for these guys. Just to say a few things, these ultraviolet, X-rays, and gamma rays are called ionizing radiation. So they're at the high frequency, and they're higher frequency than visible light. All of these guys up here are dangerous to humans, right? Because they can when you get hit by this light, it can damage, it can sort of enact chemistry on the DNA in your skin, and so this is considered dangerous dangerous radiation. And so these are monitored, and if people have sources that produce these things that are used in medical applications, helpfully for us, they're monitored carefully. The stuff below visible is pretty not dangerous, pretty safe. And in fact, you'll often hear people saying cell phones cause cancer, and it's just not true, or there's very little evidence for it. Cell phones typically are in the microwave or radio wave range. These waves are very low energy, and so they can't damage your DNA or anything like that. They can't ionize anything to change anything's chemistry, and so it's very unlikely that you're going to get hurt by your cell phone. So this is an interesting picture of all the bands of the electromagnetic spectrum and how they penetrate the atmosphere. And so if you'll notice, here's the ground here, right? Not much gets to the ground. All these high energy ones have been filtered out of the atmosphere on their way to the surface of the earth, right? Most of these are emitted by the sun that we get for one reason or another. The sun produces these. The whole spectrum there, all the way across. Most of these energetic ones, lucky for us, can't get through the atmosphere. They just lose all their energy, and so they're harmless to us. This region here is where the ultraviolet is, and most of that gets filtered out. A little bit gets through, and so you have to be careful to wear your sunscreen or a hat or something like that. Look how the visible is right in the middle of this section that gets through. Some of the ultraviolet gets through, and then there's an area in the ultraviolet that's blanked out, right, that doesn't get through. This is at least part of the light that contributes to the greenhouse effect. which is trapping radiation near the surface of the Earth. And then, but a lot of radio waves do go right through the atmosphere, and so this is why they're so useful for communication. We can shoot them to antennas a long way away, and they'll just travel right through the air like it's not there. Super long wavelength radio waves do not. So you can see that it wouldn't be useful to build a telescope for these wavelength ranges and leave it on the surface of the Earth, because none of the light gets through. And so if you want to build an X-ray telescope or a gamma ray telescope or an ultraviolet light telescope, you want to put those in space so they're not looking through the atmosphere. So here's some basic questions. What are the two basic types of waves? What is the difference between transverse and longitudinal waves? List 4 basic properties of waves. And what are those basic properties? What band of the electromagnetic spectrum has the fastest speed in a vacuum? That's kind of a trick question. List the bands of the electromagnetic spectrum in order of increasing wavelength. List them in order of increasing frequency. What's the period of an electromagnetic wave that has a frequency of 200,000 hertz? So you would have to take 1 over that, right? What bands of the electromagnetic spectrum do not reach the ground? What bands partially reach the ground? I think that's it. Okay.